Melissa, and I will be talking about the Haber process today. The Haber process, also known as the Haber-Bosch process, is a method of synthesizing ammonia from nitrogen and hydrogen gas under high pressure and temperature, using an iron catalyst. This chemical reaction is fundamental in the production of ammonia, which serves as a critical component for fertilizers and industrial chemicals. The Haber process has revolutionized agriculture by providing an efficient way to produce ammonia on a large scale, making synthetic fertilizers widely available. This advancement has increased agricultural productivity and supports the global population's nutritional needs. Before the development of the Haber process, the world relied on naturally occurring sources of nitrogen, such as guano and nitrate deposits, which were limited and geographically concentrated. Before this invention, the world faced a potential shortage of naturally occurring nitrogen compounds essential for fertilizer production, which could have limited global food production significantly. The invention of the Haber process by Fritz Haber and Carl Bosch in the early 1900s provided a sustainable and almost limitless source of nitrogen by fixing atmospheric nitrogen, which consists of approximately 78% of the air. This breakthrough earned Fritz Haber the Nobel Prize in Chemistry in 1918 and has since been considered one of the most important technological achievements of the 20th century. The global importance of the Haber process extends beyond the agricultural to various industrial applications, including the production of plastics, explosives, and pharmaceuticals. It's been estimated that the process is responsible for sustaining nearly half of the global population's food supply. Understanding the kinetics, thermodynamics, and equilibrium conditions that govern the synthesis of ammonia is important for optimizing the process, enhancing efficiency, and minimizing environmental impacts. We'll also evaluate the patentability of the process considering its historical context, the principles of patent law, and the technological advancements that have emerged since its invention. This examination will highlight the scientific ingenuity behind the Haber process and explore the legal and ethical aspects of patenting chemical processes that have a huge impact on global food security and industrial practices. The process is conducted at a high temperature in the range of 450 to 500 degrees Celsius. This elevated temperature increases the reaction rate. While higher temperatures favor faster kinetics, they also shift the equilibrium toward the reactants, which are the nitrogen and hydrogen gases. So high temperatures are used to increase the kinetic energy of the nitrogen and hydrogen molecules. This results in a greater number of molecules having the minimum amount of energy required to overcome the activation energy barrier for the reaction to occur. The reaction occurs under high pressure, usually between 150 to 200 atmospheres. High pressure favors the forward reaction, which produces ammonia, because it shifts the equilibrium toward the side of the fewer gas molecules. According to the ideal gas law, reducing the volume or increasing pressure will shift the balance toward fewer moles of gas, in this case favoring the formation of ammonia, which has a smaller volume compared to the sum of the reactant gases. An iron catalyst is used to lower the activation energy of the reaction, making it easier for the nitrogen and hydrogen molecules to react and form ammonia. The catalyst is typically enhanced with several promoters to improve its efficiency and durability, such as potassium and aluminum oxides. These promoters increase the catalyst's surface area and prevent it from becoming poisoned by impurities and consumed in the reaction. It provides an alternative reaction pathway with a significantly lower activation energy compared to the reaction proceeding without a catalyst. This means that more molecules have sufficient energy to react at a given temperature, thus increasing the rate of reaction. The kinetics of the Haber process is influenced by temperature and the presence of a catalyst. Both of these factors play a role in determining the efficiency and yield of ammonia synthesis from nitrogen and hydrogen gases. Improving reaction efficiency is done by lowering the activation energy. The catalyst allows the reaction to proceed quickly at relatively lower temperatures than would otherwise be required for a comparable rate of reaction without it. This makes the Haber process economically viable and environmentally more acceptable, as it reduces energy consumption and costs. The catalyst is selective. It accelerates the synthesis of ammonia from nitrogen and hydrogen without favoring unwanted side reactions. This selectivity is necessary for achieving high yields of ammonia. The Haber process is exothermic. The reaction releases energy because the bonds formed in the product are stronger than the bonds in the reactants, leading to a net release of energy. Increasing the temperature shifts the equilibrium toward the reactants because the reaction is exothermic. Decreasing the temperature favors the formation of ammonia, shifting the equilibrium towards the products. Therefore, a compromised temperature between 450 and 500 degrees Celsius is chosen to balance a reasonably fast reaction rate with a satisfactory yield of ammonia. High pressures are used in the Haber process to shift the equilibrium towards the products, increasing ammonia yields. However, extremely high pressures require expensive equipment and more energy, leading to higher costs. Because of this, the pressure is optimized to achieve an economically viable balance between equipment costs and ammonia production efficiency. At the time of its development, the Haber process represented a groundbreaking scientific achievement. The ability to synthesize ammonia from atmospheric nitrogen and hydrogen gas was not only unique but also solved the global challenge of producing enough nitrogen fertilizers to support agriculture. The method required insights into reaction kinetics and the effects of pressure and temperature on chemical equilibrium that were not really apparent to experts in the field at the time. The Haber process had profound environmental and economic impacts. Economically, it allowed for the large-scale, cost-effective production of ammonia, leading to the widespread availability of nitrogen-based fertilizers, which significantly increased agricultural productivity and food security worldwide. However, the environmental impact has been mixed. While it supported enhanced food production, the energy-intensive nature of the process and the potential for the nitrogen pollution through fertilizer runoff have been concerns. Despite these issues, the impact of the Haber process has been overwhelmingly positive in the terms of human welfare. Considering these aspects, the Haber process at the time of its invention clearly exhibited a high degree of novelty and non-obviousness. It addressed a significant need with profound environmental and economic impacts, despite some negative environmental consequences. The technical challenges it overcame, such as development of a suitable catalyst and the engineering feats required to operate under high pressure and temperatures, demonstrated significant innovation. Given these considerations, the Haber process's significance, innovation, and the technical solution it provided strongly merit patent approval.